last year I had this test day split up into 2 separate days. So what I did this year, because we only have 1 day for testing, is I pretty much took those 2 tests, and anything I felt like was overly challenging or a little bit convoluted, I actually put on this review packet. Whereas the more straightforward stuff that I've seen on Regencies, I like put on the test. So the test should be easier than this review packet. Some are like 6 of one, half a dozen of the other. I just kind of separated just to get one type of each question on, like this first one. So the heights of women in the United States are normally distributed with a mean of 64. So I'm immediately going to draw that. And a standard deviation of 2.75. And they're asking for the percent of women whose heights are between 64 and 69.5. When they ask you for a percentage between a certain interval, that's a norm CDF. So between 64 and 69.5, we're essentially looking for what percent of the area under the curve is there. So it's just a norm CDF. Second, there's norm CDF. My lower part of the interval is 64. My upper part of the interval is 69.5. And it is another indicator of norm CDF when they give you the mean and the standard deviation. They gave us the mean as 64 and the standard deviation was 2.75. So if we just paste that, I pasted it into Y1. Shoot. I'm going to do that again. There we go. My numbers are still there. So low to high to mean to standard deviation. Paste it into the screen, hit enter, and it's going to give you the percentage right there. And this particular question asked, what is the percent? So that's 47.7%, which is 48 to the nearest whole number. Okay, on the next one, scores on a math college entry exam are normally distributed with a mean and a standard deviation. So again, they're giving you a mean and they're giving you a standard deviation. So just to wrap my head around how this is distributed, I put the 68 in the middle. Students scoring higher than 1 standard deviation above the mean. Okay, so 1 standard deviation above the mean is going to be that 68 number plus 7.2, which is a cutoff of 75.2. So what this is telling us is that anybody who scores up here will not be tutored. No tutoring. Which means everybody down here will be tutored. So their question is, how many of the 750? So they're not asking you for the percentage anymore. They're saying how many of the 750. So we're still going to calculate the percentage, but then we have to take that percentage of 750. So how many of the 750 incoming students can be expected to be enrolled in the tutoring? These were the tutoring kids. So all of these. So I would calculate this percentage with norm CDF again. So it's a norm CDF. Your lower end here, so whereas the first one had a firm start and end to the interval, this one doesn't really have a firm start, which is where we use that negative infinity, negative 999, up to 75.2 with a mean of 68 and a standard deviation of 7.2. So second there's norm CDF, and I'm just going to plug those in. Paste it, and it's going to give me the percentage, 84%-ish. So that's 84%. This one did not ask us for the percentage. It said how many of the 750. So that would be 84% of 750. So to come up with the raw number, take that 84%, which is already on my screen, and multiply it by 750, and I'll get 631 kids, which is option 1. You have to read carefully in that one because the one sentence tells you who's not going to be taking the tutoring, and then they actually ask you for who is going to be taking the tutoring. So that's a little bit tricky the way they word it. They word one sentence as in who's going to be tutored, and then the other as who's not. Any questions? Does that make sense? Okay. So this Elizabeth in number 3 waited 6 minutes at a drive-through at her favorite fast food restaurant the last time she visited. She was upset about having to wait that long and notified the manager. The manager assured her that her experience was very unusual and that it would not happen again. Okay, so how do we tell if he's legitimately telling the truth or not? A study then of customers commissioned by this restaurant found an approximately normal distribution. The mean was 226. And the standard deviation was 38. So if I want to get a couple of standard deviations away, 226 plus 38 seconds is 264. A second standard deviation away would be adding on 38 more to that, which would be 302. Oh yeah, that's right. If I go down by 38 seconds to go one standard deviation below, 226 minus 38 will put me at 188. And down 38 more will put me at 150. So just loosely speaking, we should know that 2 standard deviations below to 2 standard deviations above is the middle 95%. So 95% of the time, people in the drive-thru should be expecting to wait between 150 and 302 seconds. Okay? She waited for 6 minutes, which 6 minutes times 60 seconds is 360 seconds. I think we can all agree that 360 seconds is way, way, way out here. It's beyond 2 standard deviations away. So is that rare? Absolutely. So to answer the question, was Elizabeth's wait time unusual? Yes, because 95% of the time, people only wait between 150 and 302 seconds. She waited for 360. So we used our 95% level of confidence because we did our 2 standard deviations on either side. Does that make sense? Okay. Okay, number 4 gives us 2 versions of a standardized test are given, an April and a May version. You might as well call these the SATs because I think that's what they're insinuating. The statistics for the April version, so I'm going to do April's statistics, show a mean of 480. I'll label this one April. And a standard deviation of 24. So I'll just write SD equals 24. In May, the mean was 510. And the standard deviation was 20. So a higher average, but a lower variation. So this is how you could and what this is going to explore is how you could kind of compare people's performances on 2 different SATs. Like some people took one in April, some people took one in May. How do you argue that someone did better? Like these people would say, okay, this person in May did better if they got a 510, but not really. A 510 in May is equivalent to a 480 in April, just because the exams aren't identical. So it's unfair to really say just because you got a 510, you did better. So they'll normalize these across different exams to kind of let everyone be compared fairly. And you kind of eliminate the discussion of, oh, your test was easier than my test. So for all intents and purposes, someone who scored a 480 in April performed just as well as someone who got a 510 in May, because they both scored on average with their peers. So in Part A, Joanne took the April version, so we're here, and scored between a 510, which is somewhere up here, and a 540. So she scored somewhere in that range. What is the probability to the nearest 10,000 that a test paper selected at random from this April version scored in the same interval? Probability, what is the percentage chance? That is a norm CDF question. So Part A would be a norm CDF. On the low end, it's a 510. On the high end, it's a 540. The mean was 480, and the standard deviation was 24. So you're just going to get your probability by doing norm CDF again. typing in those numbers, 510, 540, 480, and 24. Mrs. Hill, I'm recording a video. I'm just letting you know. Do you want me to stop by when I'm done? Okay. 0, 9, 9, tenths, hundredths, thousandths, 10,000ths. 0.0994 would be your probability to the nearest 10,000. Okay? Now, that's where Joanne scored. Maria, who took the version in May, over here, it says, in what interval must Maria score to claim that she scored just as well as Joanne? Well, Joanne's going to say, well, I scored this much above the average. We want to find out what that equivalent would be on Maria's scale. So right now, if you look at 510, and this is where z-scores are going to come back into it. 510 is how many standard deviations above the mean? Well, it's 30 points, right? And 30 points when each standard deviation is 24. That's 1.25 standard deviations. So we have to figure out over here, what is 1.5 standard deviations above the mean? And that will give us the equivalent to 510. So if your mean is 510 over here, and we want to do, did I say 1.5? It's 1.25. And we want to add on 1.25 standard deviations of 20, then that's going to be 510 plus 1.25 times 20. That's going to be a 535 score. So a 510 over here in April is equivalent to a 535 in May, arguably. They're both 1.25 standard deviations above their mean. And then we're going to do the same thing for 540. 540 is 60 points above the average. When 60 points comes from data that has a standard deviation of 24, that's 2.5 standard deviations. So in May, we want to go 2.5 standard deviations above the mean, which would be 510 plus 2.5 of these standard deviations of 20. And when I type in 510 plus 2.5 times the standard deviation of 20, that's going to give me a score of 560. So the argument would be that the interval in April from 510 to 540 is comparable to the interval in May of 535 to 560. And that would be your answer. In what interval must Maria score in May to say she did as well as Joanne? 535 to 560. Because again, the reality is you can't say, oh, Joanne scored a 510 and Joanne scored a 510, or I'm sorry, Joanne scored a 510 and Maria scored a 510. Oh, they scored the same. No, they didn't. They took different tests. So Joanne scored 1.25 standard deviations above the mean. Maria's going to have to also score 1.25 standard deviations above the mean, which would equate to a 535 in her case. So that was a sample question that the state released. It wasn't actually on an exam, but it was something they gave us to look at. On this experiment, we have group 1, which got an energy drink, and group 2, which got cola, or straight sugar. And then each individual's time to read a passage was calculated. And in group 1, all the kids that had the energy drink, it took them 17.7 seconds to read whatever passage. In the second group, here's all their individual times. On average, it took them 19.1 seconds. So it took the cola group longer to read. So you might argue that the energy drinkers did better. By how much? 19.1 minus 17.7. That's a difference of 1.4. So group 1 read approximately 1.4 seconds faster. So the group that had the energy drink as opposed to the cola read faster by 1.4 seconds. So this girl concludes that drinking energy drinks makes the students read faster. It certainly looks it. But was that 1.4 seconds due to coincidence? Or is that significantly different enough to convince us that the energy drink actually did lead to that quickness? Using information from the experimental design or the results, explain why her hypothesis might be incorrect. Couple ways you could say that. And I'm not going to write this, but you could say that a difference of 1.4 seconds could have been coincidental. It could have been coincidental that the faster readers were in the energy group. That's one way of saying it. Another way I saw accepted on this problem was that just because you had an energy drink doesn't mean that you read faster than someone with a cola drink. So if you look at individual people, here's someone who took an energy drink. It took them 17 seconds. Here's someone who drank cola. They read faster even though they drank cola. So on an individual basis, it wasn't that significant. It doesn't mean that someone who drank cola couldn't have read faster. Clearly they did. So either one of those would be a potential hypothesis as to why she might be incorrect. But we really can't tell whether or not 1.4 is significant until we look at it on a simulation. So where does 1.4 fall on this simulation chart? Right here. Which means all of these results from 1.4 and beyond, so going towards the outer part of your graph, those are all the times that it truly did happen coincidentally. Now, if you add all these up, this is 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. So 34 out of how many simulations? You look back up, 232. 34 out of 232 simulations showed a difference of 1.4 seconds or even more. 34 out of the 232 simulations showed a difference of 1.4 seconds or more. And anytime it's happening on a simulation, it's guaranteed that it was a coincidence, right? So that would be coincidentally. And what percent is that? 34 out of 232. That means 14.6% chance that this was coincidental, which is pretty high. That's definitely outside of the 95% and even outside of the 90% confidence interval. The 90% confidence interval is sometimes nicer because if it's in the middle 90%, then this is your outer 5% and this is your lower upper outer and lower outer 5%. Well, we're definitely still within that 5%. We're like 14% in. So is this result significant? No, because it's too much in the middle of the graph. The only things that are significant are going to be stuff and things out here. They give you something less than 5% of the time. So to answer the question, this girl decided that the difference in mean reading times is not unusual. That's correct. It's not overly unusual. Support her decision using the results. So using the results is me right here citing how many times out of the number of simulations this happened coincidentally. And so because it happened coincidentally 15% of the time, you could say, therefore, 1.4 is not outside of the 95% confidence interval. And you could even say 90% confidence interval because it's not outside that either. And in stats, we usually talk about the inner 95% confidence interval or the inner 90%. It probably won't hover in between those. It'll be all or nothing. It'll be either way, way, way on the outside or pretty well on the inside. So anything on that inner 90% is not significant enough to conclude anything. Okie doke. All right. Last one. Nope. All right. Similarly here, we have two groups. Group 1 got a tutor, and group 2 got an online program. Online tutor, I guess. A real tutor versus an online tutor. Okay? And then their test grades were looked at. So the mean difference in part A, group 1 minus group 2, is 80.16 minus 83.8. That's a negative 3.64. So what that means is that on average, group 1 with a real tutor performed 3.64 points less on their test. So this kind of just at face value suggests that a real tutor is worse than this online program. Now, was that coincidental, just based on the way they were grouped, or is that a significant number? Okay, so we have to see where that negative 3.64 falls on the simulator. So negative 3 would be here, negative 3.5 would be here. So we'll just assume these are all beyond negative 3.64. This bar goes up to, let's say, 6-ish, and this bar goes up to, let's say, 2-ish or 3-ish. So that's 9 total. And cite this, 9 out of 500 simulations had a difference of negative 3.64 or even more. And 9 out of 500 is 1.8%. So is that outside of your 95% confidence interval? Yes, it is. So because it's on the outskirts, that is a significant difference. So you would say the negative 3.64 is a significant difference and likely means that the online tutor is better. Or you could say likely means that the personal tutor is worse. It doesn't really matter which vantage point you phrase that from. Okay? Anything on the outskirts is significant. If you wanted to add in that it's outside the 95% confidence interval, you could use that phrase as well. But the inner 95% confidence interval is the middle 95%, which means we're looking for anything in the top 2.5% or the bottom 2.5%. And clearly 1.8 is in the bottom 2.5%. Any questions? Okay. Are you done? Yeah. All right, last two here. So we have 55 students that were going to the prom and participate in a survey about their music choice. 60% responded that a DJ would be preferred. So just in our sample, 60% was what we ran our simulation off of, because that's what our one sample showed, is that 60% wanted a DJ. So we're trying to decide, is that 60% legitimate for the population, or was that just luck of the draw of the sample we happened to take? So we ran a simulation 200 times, treating 60% as the potential population average, so no surprise this is sort of centered around 60. And it gave us a standard deviation as well. Thank you, you too. So using the results of the simulation, determine a plausible interval containing the middle 95%. That's your margin of error stuff. So that means take your average of 0.60 and add or subtract twice the standard deviation of 0.066. So 0.60 plus 2 times 0.066 gives me as high as 0.732, and 0.60 minus 2 times the standard deviation gives me something as low as 0.468. So even though the one sample said 60% wanted a DJ, that was just our sample proportion. In reality, our population is probably somewhere between 73.2% and 46.8% wanting a DJ. Our sample showed 60%, but we can conclude safely that our population would probably be somewhere between 46.8 and 73.2. So in part B, when they ask, members of the prom committee are concerned that a vote of all students would produce a 50-50 split. Is it feasible that the population might be a 50-50 split? And the answer would be yes, because 50% falls within that window. Yes, 50% falls within our confidence interval of 46.8% to 73.2%. So same idea. If you look at your middle 95%, is 50% in your middle 95%? Absolutely. Your outskirts are way down here and way up here. So that's a fair claim. It's on the low end, but it could happen. And then the last one here is just this random sample of 100 people that would best estimate the proportion of all registered voters in a district who support improvements to the high school football field should be drawn from registered voters in the district at A. So if we want to take a sample to see who's in favor of improvements at the high school, we should probably stay away from people at a football game. Because if they're at a football game, they probably support the school. If they're at a school fundraiser, they probably support the school. That would introduce a bias. If they're at a high school band concert, they're probably more likely to support the school. The only place which is truly random and independent of the school entirely, it would be if we grabbed people from a supermarket. Some of those people might be in favor of the school, some of them might not be, so it's a more fair response or a more fair place to ask them about whether or not they support the high school. Every other one of those would create a bias because every one of these is tied to